A research team puts together a study to see if students from different universities vary across time spent playing video games during any given week. The researchers randomly recruited 100 students from UCLA, UCSD, Pepperdine, CSUN, and Loyola. The researchers collected data from all of the participants and then ran various analyses to determine if the groups differ statistically. So usually when comparing groups, we use a t-test, but in this scenario, we have more than two groups, so we would be using an ANOVA test. An ANOVA test analyzes the variance statistic. An ANOVA test is the most popular multiple group significance test, and it will tell us the difference among combinations of each two groups, but it will not tell us in which group the difference is in. It is also a parametric test in which we infer and generalize. Now I'll be talking about the several components in the ANOVA output table. I'll begin by describing the between sum of squares, which we call BSS. So BSS is the comparison of group means and the one we are interested in when we are testing if time spent playing video games varies between different schools. We also have within sum of squares, which is our WSS, which is used to measure the dispersion within each group to be compared, and we consider this our error. So almost always our BSS is less than our WSS, and that's because there's different number of items acting on each. In our BSS, it is the number of we have the number of schools that are acting upon it, and our WSS, we have our sample sizes that are acting upon it. So we can't directly compare these two. So we have to find our mean square. To find our BMS, which is our between mean square, we'd have to divide our BSS by the degrees of freedom, denoted as DF. And to find our WMS, which is our within sum of squares, within mean squares, we'd have to divide our WSS by the degrees of freedom. And if our BMS is greater than our WMS, then we can conclude that our independent variable affects our dependent variable. We'd also have to find our F value, denoted F. To find this, we would have to divide our BMS by our WMS. Our BMS is our measure of effect, and our WMS is the measure of our error. So this is another example that can be found in the book. So over here we have our between groups and our within groups. So here is our sum of squares. So you can see our between groups, we have 241.95, and within groups 4,910.155. So as stated, the within groups sum of squares is almost always larger than the between groups. And over here we have our degrees of freedom. So we would divide our between groups sum of squares by 2, which would give us our between mean square, and the same thing for our within groups divided by 847, which would give us our within mean squared. And then by dividing these two, and over here you can see that the BMS is greater than the WMS, which means that the independent variable does have an effect on the dependent variable. By dividing these twos, you would get your F ratio, which is 20.868, which means that the BMS is approximately 20 times larger than the WMS. And lastly, we have our sig value, which is 0.000, which is less than our alpha value, which is 0.05, which means that we would reject the null hypothesis. Also, even though our sig value is 0.000, we're not 100% confident that there is no error, because in statistics there is always error. So now I'll be discussing on page 125, table 13.3, the multiple comparison test. So in this test we have a dependent variable, which is the approximate family income for last year, Bonferroni. So we have over here our heading group, which is our school, and we denote it as I. So I chose to do group 2, high school diploma. So our heading group is the mean that all the other groups will be being compared to. the group that we're comparing to it is some college, which is our J. So first, we need to find the mean difference, which is I minus J. So we would subtract the I mean by the J mean, which would give us negative 7.20. And this is in thousands, so this is saying that students that have some college make $7,200 more than students that only have high school diploma. Next, we'll be moving on to the standard error. So the standard error it refers to if we were to continue taking samples, what the difference would be. So in this case, we have 1.841. The next thing that we look at is our significance, which is 0.001. So we compare this to our alpha value, which is 0.05, and 0.05 is greater than 0.001. So we are confident that there is a difference. And an easier way to identify if we're confident that we have a difference is to look under the mean difference and check if there's an asterisk. And next, we'll be looking at the 95% confidence interval. As you can see, we have a lower bound and an upper bound. Our lower bound is negative 12.38 and our upper bound is negative 2.03. And when we look at this, we are identifying that we are 95% confident that our true mean lies between negative 12.38 and negative 2.03. So we can concur that there is a difference, there's a significant difference, and it is larger than when having only a high school diploma. So now we'll be taking a look at a study that I created. So we'll be looking at Pearson's R. Pearson's R is the correlation between two interval or ratio level variables. In this case, we are comparing the city crime rates per month compared to the average fear of crime rated 1 through 5 in these 4 cities. So my independent variable would be the city crime rates, and my dependent variable would be the average fear of crime rated 1 through 5. To obtain my city crime rates, I would get this from the local police stations in these cities. And for my average fear of crimes, I would have surveys for the population, and my sample size is 200. I would be choosing 50 people from each of these cities. Pearson's R is also a parametric statistic because we use interval and ratio level data. My hypothesis for this study is that as the city crime rates monthly increase, the higher the city crime rates monthly, the higher the average fear of crime would be. Our null hypothesis would be that the city crime rates do not affect the average fear of crime. So Pearson's R would be a great test for this because it would show me the correlation between the two. When finding Pearson's R, we assume many things. So to begin with the various assumptions of Pearson's R, I'd like to start off with linearity. Linearity means that we would choose the best fitting line, which is straight, to represent all our data. So for instance, if we had a plot with multiple points representing all of our data, we would have the best fitting line, because we could have another line which is not straight that may be closer to some points, but in this case, if we have the best fitting line, that line is closest to all of the points. Moving on to homoscedasticity, which is the variance for the dependent variable is equal for each value of the independent variables. Next, we have normally distributed data for both the dependent and the independent variables. We also have no outliers, and in this case you can see that we have no outliers. An outlier would mess up our whole R. And lastly, we have residual variance is uncorrelated with independent variable. So using the regression equation, which is y equals alpha plus beta times x, we can predict what will happen in the future because we will see how one of the variables will affect the other in the future. And as we can see in the scatter plot that we had drawn with our perfect line, you can see the way that it's going to go depending on how the future is going. So to find your R, you have your X components, you would sum them all up, your Y components, sum them all up, and then you would multiply your X and your Y and sum that up, giving us A. Then we would have the squares of all the X's and get the sum of that, our sum of squares. And then the same thing for our Y components and get our sum of Y's, sum of squared for Y's. And then multiplying our X squared with our Y squared, we'd obtain this number, and then we would square root that number and divide the sum of our X and Y components by that number, giving us R. So R could be negative or positive, and that would show us in which direction our correlation is going. And that doesn't mean that one is right or wrong. It would just simply mean that the dependent variable is either directly proportional or indirectly proportional to the dependent variable. Our R could be no greater than 1. A 1 would be a perfect relationship. We could also have a partial relationship, and we can have no relationship. A no relationship would just be if we had a bunch of plots and we had a straight line through the middle. Moving on to right back to our regression equation. So Y is our Y component, X is our X component. The alpha would be the intercept in where it starts, and our beta would be the slope. So using the steps that I've shown before, I solved for R, and my R ended up to be 0.5. And as stated before, my sample size is 200. So the sample size determines the significance. The correlation might seem weak, but if the sample size changes, then it would seem as if it was stronger. And if we have a smaller R squared, then our beta is not reliable. We can assume that our beta is not reliable. And if we have a larger R squared, then we would assume that our beta is reliable. And over here we have a sig value that I had made up, which is 0.004, which is less than our alpha value of 0.05. So we can reject the null hypothesis and accept my hypothesis that the city crime rates affects the average rate of crime. So here we can take a look at table 16.1, which can be found on page 152. So here we have a Pearson's R correlation, and this Pearson's R correlation is between education and crime victimization. So we have a hypothesis that people with more years of education will rate their chances of being a crime victim higher than those who have fewer years of education. So this is a positive correlation, and when I say positive correlation, we're taking a look at both of our variables, which is education and crime victimization. So when I say positive, that means that as the years of education increase, the chance that they will be victimized will also increase. So we can take a look over here. What we're given, we have Pearson's correlation, which is our R, which is stating that our R is 0.086, which shows that we do have a positive correlation. We also have our sig two-tailed, which is our probability, which is 0.003, and what this 0.003 means is that that us obtaining 0.086 by error was 0.003, and 0.003 is also less than our alpha value of 0.05, so we can reject the null hypothesis and accept our hypothesis that the more years of education, the higher chances of crime victimization. And lastly, our N is our sample size, and as you can see, our sample size is 1,147. And if you can see, this box right here is identical to this box over here. So now we need to interpret R as the strength of the relationship. So as stated before, our R is 0.086. So first we'd have to square that. So 0.086 times 0.086 will give us 0.0074. Now we'd have to multiply 0.0074 times multiply it by 100%, giving us 0.47%. So by now, what this number tells us is that by knowing years of education, we can account for 0.74% of the variation in ratings of victim chances over the next year. So our attempt to explain victim chances by education is statistically significant, but not worth much, because if we have 100% and we subtract our 0.74%, we're left off with 99.26%, which shows us that there is a lot of unexplained variance or error.